So I'm excited to be able to share, to teach you all about factor analysis. This is a quantitative approach that I've very frequently used in my work. Let me first off introduce myself, who I am. Some of you may know me, but for those who don't, my name is Manuel Gonzalez. I am an assistant professor in the Police Graduate Studies program. And some of you in the higher ed track may have also had some chances to interact with me, especially in those who are taking dissertation seminar this past year. Y'all are probably sick and tired of seeing my face, but hello. So without further ado, let's talk about factor analysis. So just a sec. And there's going to be a stata tutorial toward the end of this discussion, as well as some time for Q&A. So if you have any questions, just feel free to jot them down. But if there are any kind of burning questions that you have, if there's something like hold up, please touch on this again before we move forward. Don't hesitate to interrupt. Given teams, it's a little hard to see when hands are raised. So just feel free to shout out and be like, Manny, stop. I have a question. So to give you a heads up about the flow of today's presentation, first going to just take a step back and talk about the fundamentals. So so some considerations about when we're using surveys to measure things in general. So the notion of a survey as a measurement instrument. We'll talk about what a construct is, as well as what is dimensionality. We'll talk about how to examine dimensionality, which is kind of the primary goal of a factor analysis. We'll talk about what it is and some different types of factor analyses. And then we'll dig a bit further into the practical aspects of running a factor analysis with your data. So some baseline assumptions here. Factor analysis, you'll use it if you are doing quantitative research. So this is a quantitative approach. Particularly, it's most frequently used for survey research. Though there have been some cases where I've seen it used with other types of data, but more often than not, we're talking surveys here. So I'm going to be using that as kind of the guiding context throughout this presentation. And ultimately, it's most often some sort of self-reported survey questionnaire. Okay, and for both section 4 and 5, the EFA and CFA piece of things, I'll show you guys a stata tutorial. Full disclosure, I was trained as an SPSS guy, so I had to do a bit of self-teaching to get the hang of running these. I've run them plenty of times in SPSS, so I was able to pull up I pre-wrote some scripts for stata. So if you have any technical questions on the stata side, like what commands to run for what, if it's beyond my pre-written stuff, I will be able to check into it after the seminar and let you know. But if you have some conceptual questions, I'm happy to talk about it as well. Okay. So I'm also getting my stata chops or stata chops. I always forget which way it's pronounced. So let's first off talk about surveys as measurement instruments. So if you were to give someone a survey, more often than not, you are trying to, or whenever you measure anything really, oftentimes as a researcher, you're working in terms of finding what are called constructs. A construct is basically the theoretical equivalent of a variable. It's some sort of thing that we are trying to capture through measurement. Constructs can be as straightforward as age or race, but especially in the context of factor analysis, we're usually looking at more complex types of psychological constructs. These can be things like people's beliefs, their attitudes, their perceptions of themselves, of where they work, of who they work with, things like that. The mind is a very complex thing, and so we're ultimately trying to survey people to tap into what's going on under the surface. And I'll note, so whenever you're measuring something using a survey, best practice is start with the literature. If you have some sort of theoretical thing that you're trying to measure, how is that defined in the literature? And you want to design survey questions that tap into that. So I'm going to give an example. Let's say we're trying to use a survey to measure how committed someone is toward their organization. Maybe they're an administrator in a higher education institution. Maybe they're a teacher in a high school. How committed do they feel toward that place where they work? Now, when you're measuring this type of thing, commitment in this example, there can be a lot of complexity. So these are often complex constructs that we're trying to measure. So for example, commitment is an attitude. Sorry, I have a Roomba, which died yesterday, or quote unquote died, and it's like screaming at me to put it back on its base. So if you heard that, that's what it was. So when you're measuring attitudes, for example, they're very complex. They include things like behaviors, feelings, thoughts. For commitment, for example, you might have also things like there's a lot that makes someone committed, or people can feel committed for a lot of different reasons. They can be more emotionally committed, right? They might identify strongly with their organization. Your problems are my problems. They might feel, you might be measuring how much they feel like they belong in the organization. People might also be committed because they have no other choice, right? Like, I'm here because there's nothing else that I can really do aside from this job. Or there's a sense of obligation. I might feel guilty if I leave. But all these examples or types are part of being committed, right? And so, as I mentioned, it's complex. So it's usually hard to summarize commitment with one survey question. It's hard to capture all this nuance. So in practice, what we're usually doing with a survey is we're using multiple items that tap into different pieces of this construct that we're trying to measure. And so these items you might have like Likert type scales. So on a scale from 1 to 5, 1 being strongly disagree, 5 being strongly agree, how much do you agree or disagree with each of these statements about your organization, for example. And what you're doing is you're using each of these items to tap into a different part of that construct. Right? So we need multiple items to capture the complexity of what we're trying to ultimately get at with our survey measures. And so oftentimes, so some of you, if you've taken like a research methods course or an intro stats course, you might be familiar with the notion of internal consistency reliability. The basic notion here, for those who are not familiar, is if you're measuring, if you have several survey items that are all supposed to measure the same thing, the same construct, then you would expect participants to respond in a fairly consistent way across all those items. So if someone is strongly agreeing to one commitment item, you would probably expect them to agree to some extent, at least, with all the other commitment items. You're looking for that consistent pattern across. And again, that's assuming that all those items are measuring that same thing. And vice versa, if someone disagrees with the item, you might expect lower responses on everything, but you're looking for consistency. And this might be, for those of you who've heard of Cronbach's alpha, that's a way of assessing how well all of your items are measuring that one same thing. How well are these items essentially correlating with each other? But for those of you who have learned about internal consistency, reliability, about Cronbach's alpha, or you've read in the literature, the assumption that you're making when you do this is that all of your items are only capturing one thing. It leaves open the question as to, well, what if my items are actually measuring multiple constructs instead of just one? And this is where dimensionality comes into play. Sometimes we actually have several dimensions or factors in our data. I'm using these terms interchangeably, dimension and factor. And by that, I'm referring to a unique construct that might be grouped under some sort of broader construct. So if we were to look at organizational commitment, for example, and I'm pulling this from an example that I've seen in the literature, so I'm pulling from an actual set of factors that have been found and documented plenty of times in the past. Organizational commitment can be boiled down to different types of commitment, different types of dimensions or factors. You might have affective commitment, how emotionally committed we are to our organization. You might have continuance commitment. So are we committed because we feel like we have no other choice, like we have to be here, whether we like it or not? And then normative commitment, that I feel this sort of sense of responsibility to be here, regardless of whether I actually want to. Like I feel like I have to be loyal, or I feel like I would feel too guilty if I wasn't here. And these different dimensions, they're all types of commitment, so they might still correlate with each other. If you were to look at them, if you were to find them in your data or measure them in your data, but they also share this commonality of belonging to this same higher order thing. This is what's known as a factor structure. So you may have some sort of broader umbrella concept that you're trying to measure, but you may also have these more specific aspects of that broader umbrella that may come out in your data. And I give organizational commitment as an example, but you can find factor structures for all kinds of different concepts. And so for context, I'm an organizational psychologist, so a lot of the examples I'm going to give are organizational in nature. So for example, if you had like job satisfaction, you might find different factors or dimensions for satisfaction with your pay, satisfaction for who you with who you work with, satisfaction with your career growth potential. So you might find that even though they all kind of fit under this broader umbrella, there are distinct dimensions that come out that all correspond with that broader umbrella. And so you may think that you're measuring this one concept with all these items, but in reality, you might actually have subsets of items that are measuring these specific dimensions or factors. We might see that some of these items might tend to group together with each other. So participants might answer some sets of items more similarly than other sets. And some of these sets of items might even have more or higher levels of internal consistency than the overall scale. So you might see, for example, some items that reflect affective commitment. This organization has a great deal of personal meaning to me, or I'd be very happy to spend the rest of my career here. You might have some items that more clearly map onto continuance commitment. So it would be very hard to leave right now, even if I wanted to, or if I hadn't already put so much of myself into this place, I might consider working elsewhere. And then you might have some items reflecting normative commitment. I'd feel guilty if I left right now, or I owe a great deal to this place, right? You see that there's some conceptual similarity in the items themselves. So how do we know what items are grouping together? Do these smaller groups of items exist in my survey data if I were to use some existing scale, or maybe if I'm not using an existing scale, if I'm creating items on my own, am I going to find some sort of dimensionality in my data? Well, this brings us to factor analysis, which is our way of examining whether there's some sort of dimensionality in our data. So first, high level, what is factor analysis? You're basically determining whether your survey items are measuring multiple distinct constructs. And statistically, what's going on under the surface, we're not going to go into like calculations and computations. Like I'm not going to drown you in equations here. What's really going on under the surface is you're looking at how items covary with each other. Covariance is basically like an unstandardized type of correlation. If I respond highly to one item, do I respond similarly to another item? And you're looking at that pattern across all of your items in your scale and seeing if some items have stronger covariances together than others. And you're pulling that out. So you might find that out of let's say you have a 10 item commitment scale, you find that items 1, 3, and 4, 1, 4, and 9, like not even reading my own numbers, 1, 4, and 9 reflect one construct. You see that they tend to group together tightly. Items 2, 3, and 8 tend to group together tightly. And then 5, 6, 7, and 10 tend to group together tightly. So you might think that each of them reflect. Yeah, what's up?
So when you're dealing with surveys, there are times, how can you account for people who are just taking it and they don't care? Because when you're thinking of a survey and you're given the choice of highly or strongly agree, neutral, and then down the list, some people will just go straight down the middle. So how do you account for stuff like that when you're dealing with people who may not take the survey seriously versus those that do?
That is a great question. So I'll try to have a concise response to that, though I could have an entire other seminar on careless responding. There's a ton of research out there on different ways to detect and handle what is known as careless responding or insufficient effort responding. Some ways you can overcome it or ensure sufficient motivation when people are doing surveys is methodological in nature. So you can, for example, make sure your surveys are relatively short. So especially if it's not a paid survey, if it's voluntary, having fewer items can help to kind of make people not rely as heavily on just kind of clicking through, especially like you get to page 10 out of 20 and you're like, I'm done. I need to get this thing done and get back to work. Click, 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 click. There are some statistical ways to do it as well. I don't have the script on hand, but there are ways that you can look and see if people just have how much their responses vary from item to item. So if they were clicking just straight down the middle, there would be zero variability as they go from one item to the next. No matter what question, it's just 3, 3, 3, 3, 3, 3, 3, 3. So there are algorithms you can use in SPSS or in Stata that can compute that for you, and you can remove people after the fact. So like almost exclude them from the analysis if they have too small variability. Another way that I've done is I've used, especially for like, this is especially with like paid research, if it's voluntary, if people there might be a little bit more offense to it, but if you're doing like paid survey research, I use what's called an attention check or attention check questions, where you ask people some similar or some kind of odd questions, or even just very straightforward, like select strongly disagree if you are paying attention. And you'd usually have some sort of explanation in the beginning, like, for example, like we're going to have some attention checks here to just ensure that our data is sufficient quality. You will still get paid if you do the survey, but you might see these questions and that's what purpose they serve. So it like makes participants a bit more vigilant. And the last of which I'll touch on is what's known as reverse scoring. So you might have some items that are conceptual opposites, where lower scores on the item reflect higher levels of the construct. So here you might have, let's say you have affective commitment. You might have one item that's like, I feel a strong sense of belonging here, or I feel emotionally attached to my organization. A reverse scored item might be like, I hate this place. So if someone is just inattentively clicking through, and let's say they choose like, let's say hopefully they're not in the middle of the scale, it's a little harder to tell, but if they're on like the higher or lower end, you might find that someone who selected strongly disagree to I feel attached here might also, if they select strongly disagree to I hate this place as well, something might be up, because you would expect based on the notion of reliability that there would be some consistency there. So those might be some ways to, after the fact, after your data have been collected, identify those folks and pull them out of the data set, like pull their responses out before you run your analyses. So that way the data going into the analysis is of higher quality. But yeah, there's so much more beyond the surface, like under the surface to that. But this is kind of like my sort of like the best practice, high level kind of conversation about that I can give. Did that help?
Yes, thank you.
Awesome. Great question. Okay, so when you're running a factor analysis, let me also touch on sort of the practical benefit of running a factor analysis. Like, why should we care if there are factors in our data? The great thing, the major benefit about factor analysis is you're taking many items and turning them into a few variables. So for each of these, say you have these 10 items, and you find that, let's say you do a factor analysis and it says you have these 3 factors in your data, you can, instead of analyzing 10 items separately, you can actually just average the items belonging to each construct together. So I might average people's responses to items 1, 4, and 9 and make a new variable reflecting the first construct. I'll average items 2, 3, and 8 and make a new variable for the second construct. And then same thing for construct 3. So now instead of 10 survey items, you have 3 variables to analyze that are just the averages of their respective items. So it makes your data and your analyses a lot more manageable, because you're looking at kind of these more aggregate level variables that encompass multiple items, rather than looking at one item at a time over and over again. You have like a mile-long correlation table, and you're like, wow, there's way too many Pearson's R's here. How do I interpret all this? My head's going to explode. You make it a lot more manageable for yourself as a researcher. And by turning them into these kinds of more aggregate level variables that reflect specific constructs, it's a lot more interpretable, your data. You can get a clearer sense as to what broad theoretical thing you're trying to measure there. And so the example I've been giving so far, it's It's an example in which we know what construct we're measuring in advance, in this case, organizational commitment. So for example, you might have seen a scale for the concept you're interested in measuring out in the broader research literature. You get permission to use it, and now you're using it in your study. And you may know from past research using that same scale what has been found. That's one example, and that maps onto the example I've been giving so far. But sometimes it's not the case. So for example, you might create your own survey items, and then after the fact, you might want to determine whether some of these items are measuring distinct constructs, because in this case, you're kind of starting from scratch. Factor analysis is also suitable in that regard. We'll talk about some different approaches literally in the next slide. There are two approaches to factor analysis that we'll cover: the exploratory approach and the confirmatory approach. So exploratory factor analysis, or EFA, confirmatory factor analysis, or CFA. I'll be using those acronyms moving forward because those are a mouthful to say repeatedly. So each of these types of analyses have their own kind of underlying goal. When you run them in Stata or SPSS or R or whatever statistical software you have. For EFA, your goal is you're telling the statistical program, dig into the data and just tell me what factors come up. And you would usually use EFA if either you don't know what factors are being measured, right? So you don't have any kind of in advance rationale for what's going to come out of your data. You might have some suspicions as to what might come up, but you don't really know exactly what's going to pan out factor-wise or how certain items might actually wind up grouping together. And you're trying to just basically get Stata to tell you. Or if you have a factor structure in mind that you think exists will emerge, and you want to see if the software finds it without you specifically telling it to do so. Like basically go forth and let me see if you replicate exactly what I think is going to happen. But you're exploring here. You're letting the software program find the factor structure for you. Confirmatory factor analysis is the opposite. This is when you think that a specific factor structure exists. Let's say organizational commitment. I go in and I know that at least I have strong reason to believe there will be an affective commitment factor, a continuance commitment factor, and a normative commitment factor. And you check and you basically tell SPSS or Stata, this is the factor structure. Do the data support that exists? You're testing it out. So in this case, for CFA, you already know or have an idea about A, what factors are being measured with your scale or with your survey, and this is another core part, which items measure which factors. So you might know that items 1, 4, and 9 measure affective commitment, for example, and you're telling us your software, these are the items that correspond with this factor. So the big differences are exploratory factor analysis. You are exploring what factor structure is out there. You're just trying to search for the factor structure. Confirmatory factor analysis, you're confirming what structure you think exists. Okay, so now we're going to go into the how-to piece, right? So we've kind of covered at a broad level what this is all about. We'll now touch on the different steps. So I'll give you the rundown for EFA first, and then we'll go through a Stata tutorial. And then after that, we'll touch on CFA, and then we'll go through another Stata tutorial. All right, EFA. So you've collected your data at this point when we're talking about this setup phase, right? So here are the core steps for setting up your analysis first. So if you're punching in syntax, for example, into Stata, or if you're going through the guided user interface for SPSS, step one is you select what survey items to use for your factor analysis. Now, you don't necessarily, for your EFA specifically, you don't necessarily need to take every one of your survey items and dump them into the analysis. And I would actually advise against that, because the more and more items you throw into the analysis, if you have a 70 item survey and you're trying to shove all 70 items in there and see what factors pan out, that's a lot of covariance for the software program to sift through. And you might get some oddly interpretable factors there. You might find some strange factors that may covary due to chance or just by some other kind of statistical artifact. Usually you want to select groups of items for your analysis. based on maybe some initial commonality between them. So let's go back to an earlier example. Say we're surveying administrators in a higher education institution. And we have a bunch of questions, not just organizational commitment, but a bunch of questions that are asking them about how they feel about their university or college. So those all have some sort of commonality to them. There's a common target. You're also getting the participants' perceptions of that target, the organization. And so you might select those items for your analysis. I'll note that when you're doing an EFA, your items should ideally be on the same Likert type scale. This should be continuous type data, or for Likert type, you can argue it's like ordinal, but you can essentially treat it as continuous type data. They should be have the same number of scale points. So a 1 is like, let's say a 1 is the minimum and the 5 is the maximum, for example, or everything's on a 7-point scale. And ideally, they should have the same response anchors. So like if like all of them being strongly agree, strongly disagree, or all of them being not at all to a great extent. The reason why is, so first, if they have a different numbers of scale points, it's like comparing apples and oranges. It's harder for the system to kind of check the covariance properly, because it's assuming that they're all on the same scale length. If you use different response anchors, then it's more of an interpretability issue. It's kind of, well, you're agreeing and disagreeing to these, and these are, you're talking about to a great extent or not at all. Like, are these really conceptually the same ways of capturing that construct? Right. So ideally, they should be similarly formatted, the items you choose for your analysis. After you've selected your items, you choose what's called an extraction method. This is basically where you're telling the software program how to take out or how to look for factors in your items. There are a few different approaches. Well, there are a bunch of different approaches, but I'll cover the 3 most popular kinds. There's PCA, or principal components analysis. There's maximum likelihood, or ML, and then there's principal axis factors, or it's also called principal factors. It depends on which software program you use. Stata uses principal factors, or it calls it principal factors, or PF. So I'll be using that term moving forward. So PCA is typically programmed in as the default for most software programs, for Stata, for SPSS. If you run a factor analysis and you don't specify what type of extraction method, the system will usually default to PCA. The goal of PCA is to try to explain as much variance between your items as possible, while also giving you the fewest possible factors. So it's this kind of lean, efficient way of just trying to explain as much as possible, but just give me as few as possible variables or factors. There's some debate about how good PCA is. I'm not going to dive into that debate. It's just generally about whether it's appropriate to just try and explain all variance as like the sole goal, or trying to minimize factors as a sole goal. Sometimes it might be seen as too restrictive to even kind of say, like, force your data to only give you a couple factors. So maximum likelihood and principal factors tend to be more of a neutral approach for extracting factors from your data. The key difference between those two is just what you're assuming about responses on your survey items. If you're doing maximum likelihood, it assumes that responses on your survey items are normally distributed, so that there's a clear mean, there's reasonable amount of variability above and below the mean on each of those items, whereas principal factors assumes that's not the case. Maybe some of your items are highly skewed, where everyone is strongly disagreeing, or maybe highly kurtotic, where everyone groups around just one scale point with little variability around it, or bimodal, maybe a lot of people are strongly disagreeing, but you have a lot of people who are also strongly agreeing without much in the middle. The commonality is that they don't really fall in a normal curve on those items. So because of that, principal factors is designed to accommodate for that non-normality. I'll typically use maximum likelihood. It's just my kind of personal preference. I haven't seen too much in terms of people getting dinged for using principal components analysis, or really principal factors I'd only recommend if you have non-normal. If you check the descriptives for your items and you see that there's not a normal distribution on a bunch of them. So you choose your extraction method. In this case, I'd say most commonly PCA or ML. And then you can do, this is partly optional. You can do what's called a rotation. So rotation is about increasing the interpretability of the factors that you get out of your data. So let's say we ran our extraction method and we have two factors, X and Y. And we want to map out how each item in your survey or in that factor analysis loads onto each of those factors using a scatter plot. Right, so and this is basically reflecting the weight of each item on each factor. So items that group more closely to the X factor are more likely to be part of that X factor. Those grouping more closely to the Y axis are more likely to be part of that Y factor. But you notice that there's still a lot of variability around these points. Rotation is about you're essentially taking those two axes and you're literally rotating them in a way that best captures the ways that these variables, these items relate to their corresponding factor. Okay, so you're basically adjusting how much weight you give to each item on each specific factor in order to make it more interpretable. Essentially, you can use rotation to tell the statistical software how correlated or uncorrelated you would like your factors to be as well. So there are different rotation types. So you can look up, so these are the three most common categories. There's orthogonal, oblique, and then direct Obermann. If you are using a rotation, orthogonal, you're basically telling your system that you don't want your factors, whatever factors are out there, to be correlated. Maybe you want as distinct factors as possible. So whatever factors you give me from this analysis, use rotation and make them as uncorrelated as you can. Most likely there will still be some correlation, but it'll usually be much weaker. Whereas oblique, you're assuming that your factors are correlated. Typically, you would choose which one based on like theoretical rationale. Maybe like with commitment, for example, well, all these are referring to people's commitment toward their organization. So I'd probably run an oblique rotation because I expect each factor to correlate with each other because they're all types of commitment. And then direct Obermann is kind of a balance between the two. You're trying to minimize the correlation between the factors. You're trying to make them as distinct from each other as possible, but you're still allowing there to be some degree of correlation. So direct Obermann is kind of a healthy balance. I tend to use that approach, that rotation, direct Obermann, the most. But it also aligns with just the type of research that I do. I do a lot of emotion research, and when you're doing that, people are reacting toward the same stimulus. And so you'd expect there to be some degree of correlation between whatever pops up. And then lastly, and this is if applicable, you can specify how many factors you want the analysis to give you. This would usually be based on some sort of prior rationale. Otherwise, I feel like you'd wind up being a little too restrictive. So you might say, like, give me only 3 factors max, or give me only 2 factors out of this analysis. You can specify that in the software. Now you've set up the analysis. And now you have to interpret the results. Some things you'll want to do is first off examine what are called communalities and uniqueness. Basically, how much variance in the score on each item is explained by the factors. So in other words, how well are the factors doing in explaining how people vary and how they respond to the items. And then uniqueness is literally how unique is this item from those factors. Is it distinct enough to not really be explained well by them? You'll check what's called eigenvalues. So this is basically how much variance across all of your items does each individual factor explain. As a rule of thumb, you'll usually keep a factor, or you'll treat a factor as something that you'll want to examine if the eigenvalue is at least 1, that value. They can go, I don't think there is an upward limit, but usually if you have an eigenvalue for a factor that's below 1, you probably won't want to use it. You can treat it as uninterpretable, or maybe just kind of a nonsensical factor, or by chance. 1 would basically mean that the factor explains at least as much variance as an individual item would. If it's less than that, then it means it's not doing as well as even 1 item in your survey. And then lastly, you review how items load onto each factor, especially if there's a rotated solution. You want to see what items are grouping together and how are these items similar. You might look at how they're worded, for example, and see if there's some commonality between them. Well, all these items talk about people staying on the job. So maybe this is a turnover factor or like a retention factor, right? So you're looking at how these items are similar in a conceptual sense to get a sense of what each factor means, because the software doesn't tell you what each factor means. It just tells you what items group together. It's up to you as the researcher to interpret those items. Okay, so now let us talk. I know I walked you through conceptually what goes on. Let's actually go through an EFA ourselves. So to do that, I'm going to pull up Stata. Hang tight. Here we go. So I've already preloaded some data in. This is secondary data. It's from the, what's it called? The Health and Retirement Survey. This is a longitudinal study. Every 4 years, they survey a cohort of older adults in the U.S. And they survey them on a ton of different things. Their like family life, their work life, their personality. So you get tons and tons of data every 4 years on this cohort that gets followed. So I pulled in some data from that study. And for anyone who's interested in it, it is a freely available data set. So you can literally just go in and download it for any data junkies out there like myself. So I just focused in on the 2008 survey year. And I pulled in some different survey scales. So there's some personality data that are in there that I'll be using for this demonstration. So these are scales from what's called the Big 5 Personality Inventory. So there are scales here measuring what's called, or at least they're based on broader research, measuring how neurotic someone is or how emotionally unstable someone tends to be. Extroversion, so how outgoing or talkative or friendly someone tends to be. And then agreeableness, how much people tend to value interpersonal relationships and friendship and tend to be kind of a bit more, they value social harmony a lot. That's an agreeable person. So we'll be using items from those scales for our EFA here. Like I said, because I kind of taught myself how to do this, since I'm a little bit used to SPSS, I have pre-generated, I wrote out the syntax in advance. I'll be copy pasting it in. So I've loaded already the data, so you should have loaded it. Ultimately, you want to make sure it's clean. You check over you remove any responses that shouldn't be there. You check and make sure there are no weird values in your data. So if it's a 1 to 5 scale, you shouldn't be seeing any 99s or 7s or 12s. So you clean out the data set. To run a factor analysis, you type in, and I apologize if the screen is a little bit small. I can't find a way to zoom in Stata, but your syntax would basically be factor, space, and then in this case, my items are all in a row. So I'm going to start with the first neuroticism item, NEUR081. You do a little hyphen and you say, and then I go to the last agreeableness item, agree 085. So I'm telling Stata to factor analyze all the items from neuroticism, the first neuroticism item to the last agreeableness item. And then I indicate what type of extraction method I want. So I have here, you do a comma after the items that you select, and then I have ML, that's my extraction method, maximum likelihood in this case. If you were doing principal factors, so if you have non-normal data, you would write PF. And if you were doing principal components analysis, in here it's called principal factors components or something like that, it's PFC. That you write if you wanted to do like a principal components analysis, PFC. So you replace ML with either of those two. Okay, so we'll run it. Scroll up here. So this is like it's basically each iteration is kind of like it's checking the data over and over again to see like, does this factor work? Does this structure work? Does this structure work? And it kind of goes over it again and again. Then it arrives at a number of factors. It checks them again, and it brings us to our output. So first, you get a table of here are the factors that you get from your data. So factor 1, and it'll tell you the eigenvalues. So remember, eigenvalues are basically how much variance is being explained in all by each individual factor. And usually, if you want to retain a factor, you're looking for an eigenvalue of 1 or higher. So factors 1, 2, and 4 actually seem to be the only ones that would have eigenvalues greater than 1. I would probably only look at those 3. generally speaking. So it tells you a number of factors to look at. It tells you how much variance each of them explain. It tells you the cumulative amount of variance as you go from one factor to the next. So factor 1 explains 35% of the variance. Factors 1 and 2 explain 49%, and adds and adds and adds and adds until you get to the last factor. And now it tells you what factors are out there. You then go to this loadings matrix to see which items correspond to which factors. We'll focus on factors 1, 2, and 4 for the purpose of our analysis. So typically the higher the value here, the more that a given item corresponds to a given factor. So here we see, for example, if we look kind of generally speaking by theme, you see that there's not much loading in terms of neuroticism items. They're very close to 0, in some cases even slightly negative. Extroversion, there are some items here. And then agreeableness, there's kind of more consistently higher loadings. Usually like loadings of 3 or 4 or higher tends to be a good sign for whether an item represents a given factor. And sometimes, as we'll see, some items will load onto multiple factors. Usually go with the item with the factor that it loads best on. But here, this is actually kind of cool because it shows us that some of these extroversion items also are loading onto what I would interpret as an agreeableness factor, where all the agreeableness items tend to most consistently load on. And then if we look at 2, we'll see some loadings for extroversion as well. This is another case where it's kind of like, the loadings are a little weak, but you have a couple items that seem to load fairly strong. The first and the fifth items. One has a 0.35 loading, the other has a 0.96 loading. And then if we go to factor 4, this I would call our neuroticism factor. Everything loads at 0.3 or higher from the neuroticism scale. All the items, some of the extroversion items load negatively on it, meaning lower levels of those items reflects higher levels of neuroticism. And then the agreeableness items virtually don't load onto it. The next thing you would do, and again, you can constrict the number of factors as well, like I said. So if we were to run the same script, and if you were, after the extraction method, if you were to add a space afterward and put factors, parentheses, and then the number of factors that you want, you can constrain it that way and it'll just spit out 3 factors for you. But I don't really like doing that because, as you can see, it retained the one factor it retained factor 3 instead of factor 4, which, as we talked about, has a pretty poor eigenvalue. You can do rotation as well. So I'll give an example of an orthogonal rotation. If you just do dot, after you've run the analysis, if you do dot space rotate, it'll default to an orthogonal rotation. But if you want to do an oblique rotation, which again is if you want the factors to be correlated or if you want to allow them to be correlated, you would add a comma after rotate and then type oblimin oblique. And that would give you an oblique rotation. If you want to do just direct oblimin, which is a balance between the two, and then you just write oblimin and it'll give you that. But for simplicity, let's do an orthogonal because that'll give us the most distinct factors. So you're taking these factors, these 3 factors from this previous analysis, and you're rotating them as much as you can. And what we'll mostly be interested in are the rotated factor loadings and the factor rotation matrix. So as you'll see here, now that we've rotated, we have even stronger loadings for agreeableness on the agreeableness factor. We have even stronger loadings for extroversion on the extroversion factor, though we were still seeing some items that are kind of going into each factor that are spilling over. And then we have even higher loadings for neuroticism items on the neuroticism factor. So it's made them more distinct. And if we look at the factor rotation matrix, you'll see that it tried to keep the covariances between each factor as low as possible. But to some extent, it's hard to do that, especially if things are just conceptually highly correlated with each other. And so if you've done this now and you want to go, okay, well, now how do I create the factor, right? So let's say neuroticism. We have a pretty clear sense that these items reflect neuroticism. The way you do it is you average those items together. So you in Stata, you type generate, You add a space, you add a label for what the new variable is. In this case, I'm just going to call it NEUR for neuroticism, and it equals, and I'll add each item together. So item 1 plus item 2 plus item 3 plus item 4, and then I'll divide by 4. I'll get the average that way, and this neuroticism variable that gets created, that'll be my new composite variable for neuroticism. Rather than using any of those individual items for analyses, I can just use this new variable that I created. Okay, so that is EFA. Now let me talk really quick about CFA, and I'll do another Stata tutorial, and then we'll open it up to a couple questions. Okay. So CFA, for context, confirmatory factor analysis. This is a type of structural equation modeling. So anyone who's heard of SEM, CFA falls within that family. The way you set it up is you're literally telling the software program what items you want to look at, how exactly everything relates. So you may select your survey items for your analysis. Similar idea as with the EFA. You choose your set of items. These are called, in SEM language, observed variables. These are the kinds of things that you are actually getting direct responses on. Then you tell the software program to create what are called latent variables. These are the constructs that you think certain items represent. So you have your survey items, which are your actual responses, and then you're basically telling the software program, these are the theoretical variables that I want you to map some of these items onto, also known as factors. You're telling the software which items correspond to which latent variables. So items 1, so neuroticism items 1, 2, 3, and 4 correspond to the neuroticism latent variable. Agreeableness items 1, 2, 3, 4, and 5 correspond to the agreeableness latent variable. So you're telling it exactly how everything relates. And then if there are any additional relationships that you want to add into there, like maybe, like we saw, some of the extroversion items and the agreeableness items, they kind of cross over. You might tell the software program that as well. So it can account for that everything doesn't necessarily neatly map onto what we think it does. But the point here is you're usually being very explicit about how things are going to look, how your factor structure is going to look. In terms of interpreting the results, the core steps that you'll have here is, first, you'll check what are called fit indices. There are a bunch of them. These are the most common ones, and this applies to most structural equation modeling, not just CFA. You'll get what's called a chi-square test. It should be non-significant. That's like an ideal thing, but a lot of times it's not. A lot of times it is significant, which some say is problematic. Some say it's okay to ignore it. There's a lot of debate about it. You'll get what's called a CFI value for your model. So if you ideally want that to be above 0.90, and even more ideally above 0.95. If you have a CFI above that, that's a good sign that the factor structure you're saying exists is supported by your data. And then RMSEA, SRMR, they're a mouthful to say, but I'm just giving you kind of like the acronym here. Ideally, you want them to be below 0.06, each of them. And you can get like literally a table of fit indices from Stata. And one other note about fit indices, usually don't evaluate one fit index by itself. It's usually kind of a holistic assessment. So maybe some of these don't pan out and others do. It's really kind of like you're assessing the degree of fit. So maybe there's some evidence that supports it. So maybe you have, for example, a CFI that looks great, but an RMSEA that looks kind of poor. It's really your judgment as a researcher whether that's an issue or not. A lot of times, if a few indices look good, you should usually be okay to proceed with that model. You can check how the items load onto each factor, similar to like what we did with the EFA. Are there any items that don't really seem to load well onto their respective latent variable that you map them to? And then, especially if your model does not turn out to be, if the data don't support your model, you can actually check what's called a modification index, where the program can tell you what else you can do with the model you created to make it better represent or better reflect what's in the data. Okay, so I've given the steps. Now let me show you how it works. Stata time. We're going to stick with our personality variables here. Okay, so I will punch in my syntax and I'll walk you through it. So like I said, confirmatory factor analysis is a type of structural equation modeling, which Stata can do. So your opening command will be SEM, structural equation model. You add a space, and then you're basically telling Stata which items represent which factors. So I open a parenthesis here, for example, and I say agreeableness item 1, agreeableness item 2, item 3, item 4, item 5. You have a less than and a dash, so you can make like an arrow sign, and then agree. So I'm saying that these 5 agreeableness items represent the factor agree. I create a new parenthesis, and I do the same thing for neuroticism, same thing for extroversion. And a stylistic note here, and I found this out the hard way. I was like, why isn't this thing working? You're supposed to have all of your observed variables, your items, be lowercase. If otherwise, the SEM command thinks that it's a latent variable. So always use lowercase for your survey items if you're trying to do a CFA. For your latent variables or your factors, it's okay to do a capitalization, but otherwise you get an error message if you capitalize your items. And the default estimation method here is maximum likelihood. So we run our model, and depending how complex the model is or how many data points you have, it might take a while to run the model, so you have to give it a little bit of time. But it does iterations just like we said, and just like with EFA. And then you get a series of coefficients here. The first item for every latent variable is always going to be fixed to 1. But then you can interpret these are unstandardized coefficients. You can see how everything maps onto its respective latent variable. So we will scroll down, and it'll tell you whether it loads significantly onto its respective latent variable. That's the p-value over here. So ideally, you want every item that you've specified to load onto its respective latent variable to be significant. If it's not, then that means that it doesn't actually reflect the factor that you think it does. Then it gives you a bunch of variants. But the main thing I would be concerned with here is just these loadings onto these coefficients. But like I said, we need to evaluate fit. So you would punch in a follow-up command, dot space estat, E-S-T-A-T, space, and then GOF, which refers to goodness of fit. You add a comma and a space, and then stats in parentheses all. So you're just getting all the fit statistics possible. You run that and it allows you to evaluate your model. So like I said, there are 4 main things that you'll want to look for. Is the chi-square significant? It is, which is not good news, but it's not the end of the world because like I said, it's often significant. Is RMSEA less than 0.6? It's not, which is not good news. Is your CFI above 0.9 at least? It is not good news. Then SRMR down here in size of residuals, it should be less than 0.06, which it's not. So this is the case where we don't have a good fitting model. So that means that the factor structure that we think or that we've said exists, the data don't support that. So what do we do? To do that, we generate our modification indices. We go, Stata help, how do I fix this model and make it less crappy? And Stata goes, oh, here are some ideas. This whole table down here are additional things that you could do. And the higher this coefficient in this left-hand column, the more it's going to improve your model fit. Model fit, again, being an indicator of how well that factor structure actually represents the data. So to do that, let's latch on to one particular example. So here it says, well, if you tell me that your second agreeableness item correlates strongly with your second extroversion item, that would boost your fit pretty highly. You have a 123 here. It's a pretty high value. So let's try and do that. So we run our model again. This is the exact same syntax on this first line that I mentioned earlier, except at the end we had a comma, and now we're adding what's called a covariance. We're letting 2 items covary with each other. We're letting Stata know that these items are highly related with each other, and you should account for that. We're saying that agreeableness 082 is covarying highly with extroversion 082. We run it. We will run our what we're more interested in here is at least initially, does the fit improve? So we'll get our fit statistics. And even though it's not great, I'll say it's still not great. There's still probably more modifications you can do. You notice that things boost up a bit more. The RMSEA is closer to it's getting closer to 0.06. The SRMR is getting closer to 0.06. The CFI is getting closer to 0.9. So you're basically tweaking the model as you go to make it fit better. But that is how you would do a confirmatory factor analysis. And again, it's a process of just tweaking and trying to get things to fit. If nothing winds up working, then you might consider just removing a factor altogether. So like maybe because extroversion seemed to be pretty problematic, I would probably just say, well, let's leave extroversion out of the picture and just focus on agreeableness and neuroticism and see how that works. You try and rerun the model basically with a different structure. So there are some different approaches to making things look a little bit better factor-wise.